All right, so good morning and sorry for the slight delay. I hope that you are doing well. Of course, if you have any questions concerning the material that I presented last week, that I understand it's a lot of concepts maybe that you haven't seen before, but hopefully by now also the Markov chain is a bit more, it's clear for you. But again, if you have questions, we will have also some extra time, I guess, after my lecture, because I intend to just give you a few more details without digging too much into other technical aspects. But again, later on, I will be happy also, or even during the lecture, to answer your questions. So just to give you a short recap or overview, if you want, of what we did last week. So last week, essentially, we concentrated on two major problems in quantum physics, and they are connected, actually. So the first one was finding solutions to the time-independent Schrödinger's equation, and especially finding approximations for the ground state wave function, right? So if you have a Hamiltonian matrix, so we were looking for approximation for the ground state wave function psi 0, right? So this was the problem number one, and the problem number two, which is also, of course, connected. It's actually the parent of problem number one. It's the time-dependent Schrödinger's equation. So time derivative of your state should be equal to this one. Right, where C now can depend on T, and this was the time evolution of your state. Okay, so essentially we've seen that, I mean, you know that all essentially properties of quantum matter at the non-relativistic level, at least, are described by these two equations. Okay, so this is for the equilibrium ground state properties at 0 temperature, and these are for the time-dependent properties when you start from some initial state. So these are really important equations, and we really would like to find a way to solve them. As you've seen, I mean, I've discussed a few approaches, and based on the variational method. So essentially, where we, for example, work with a wave function amplitudes, with wave function amplitudes that are parameterized by some artificial neural network, right, that takes as inputs Z and depends on some possibly large set of parameters theta. And then, I mean, in the first context, we discussed strategies to find these theta that approximate the ground state. And the idea was to form this E of theta, which is the expected value of your Hamiltonian, right? And then minimize it with respect to theta. And we've shown this is strictly equal than larger or equal than E0. So we've shown that this can be written nicely as an expected value. So giving a statistical, if you want, interpretation to this of what we call the local energy, right, of my wave function. I mean, I'm not writing again this definition, but there is this beautiful connection, if you want, between quantum mechanics, expected value of quantum operators, and expected value of classical quantities on some auxiliary probability distribution, which is psi squared in this case. All right. So, and then I showed you a few techniques that you can use, especially, I mean, Markov chain, to generate samples from this P, which is again psi squared. And hopefully by now you are also more familiar with the theory behind the Markov chain that I didn't have the time to describe. So this was for the ground state. Then towards the end, last time, we discussed how to solve approximately, again, variationally dynamics. And here the situation is a bit different, because instead of looking for the time, if you want, for optimal thetas, we are actually, so when we do the time-dependent variational principle, what we are really after are the time, what we are really after is the time evolution of my variational parameters. So instead of just looking for a static, if you want, set of variational parameters that we will optimize, and they are just static ground state, we look for a set of time-dependent variational parameters that best approximates the solution to time-dependent Schrödinger's equation. And to do that, we have to write down equations for the time derivatives, if you want, of these parameters, and then integrate them in time. Okay, so this was what we did, if you want, towards the end of the lecture. And I told you that, that you have to verify, you have to essentially satisfy something like that. So you have an equation which looks like this, where S is a matrix that is related to the so-called quantum Fisher information. And then at each time step, you have to satisfy a linear system where this matrix S and this vector F can be determined again with samples. Then you solve this equation for the theta dots that are your unknowns, and then you integrate with Runge-Kutta or whatever. Okay. Good. So I hope that this is clear. The theory is relatively simple. The implementation can be quite demanding, but that's why hopefully also with Javier, you've seen some of the technical details of how this is done in Netcat, for example. And, maybe you've tried also to do by it yourself. Within Netcat, this is a nice exercise that you can try. Yeah. So today I will, what I will do is relatively light. So I will give you, as promised, instead a version of learning from experiments. Yes.
So is the ground state that you're searching for in the time-dependent equation a function of time as well?
Sorry, say that again. I didn't understand.
It's a ground state that you're still solving for a ground state?
So the ground state is what I'm looking for here, and it's a static object in the sense that it's just the one eigenstate of each, right?
And in the second one?
In the second one, here I'm solving for a state psi that depends on time.
Yes.
So I didn't write it explicitly, but this state psi now depends on time. So you have to provide an initial condition psi at time t equals 0. So this would be your known initial condition, and then you evolve that in time.
And you're also looking for like a low energy state?
No. So in this case, the energy, if the Hamiltonian does not depend on time, the energy is conserved. So the energy is the same for all states, and it's the same, at all times, and it's the same of the initial state in this specific case. This is a unitary dynamics, so it's just a rotation, if you want, of this vector without changing anything. And especially, the expected value of the Hamiltonian and everything that commutes through the Hamiltonian is conserved. Yeah. So indeed, yeah, these are two complementary aspects. The reason I was saying that one stems from two is because you can solve two by diagonalizing H and writing this equation 2 in terms of the eigenstates of the Hamiltonian, and then you have algebraic equation in terms of the coefficients of this expansion, and this will depend on time. So that's why I was saying that in a sense, equation 1 is a special case of two, but physically though, the ground state is one of special eigenstate because it's the state that is occupied at 0 temperature. So it's really the one that typically we are interested in for the low energy physics. And actually 0 temperature is not truly 0 temperature. That can be, for example, there are materials that for which 0 temperature means could mean room temperature or much higher temperature, in the sense that their energy scale is compared to the other energy scales, they are effectively at 0 temperature compared to excitation that are at much higher energy scales. Okay, so now, as promised last week, I will also tell you something, not a lot, but just a few ideas about how you can learn from experiments. So far, what I've discussed is really, yes.
Sure. So like, when we do all this sampling, like, is there like, experimentally, do we see like a lot of variance, or is it like,
Experimentally, you mean in the simulations,
In the
like in the Monte Carlo or whatever exact sampling that you might do. Okay, so this is a good point. Something that I didn't mention, and maybe it's worth mentioning since you asked, is what is known as the zero variance property. Which is something extremely useful for, especially useful for the ground state applications. But I mean, it's slightly more general. So the idea is that if you consider the local energy on a given configuration Z, right? I'm dropping now the dependence on theta because you know that the state depends on theta. So this is defined as I was mentioning in this way. So Z, H, psi, and psi is my state that depends on theta, right? Divided by Z psi. Okay, so you can see actually that immediately that if psi is equal to psi 0, so let's assume now that I've been so good at optimizing things that I found a psi that is exactly equal to psi 0, okay? Then you see immediately that E log of Z is a constant and it's equal to E0, to the exact energy. So you see this because, maybe let me just write it explicitly, but you see that I have Z H psi 0, right? Divided by Z psi 0. So you see that psi 0 now is an eigenstate of H. So I can just pull H through psi 0, and then I will get out E0 times psi 0. So you see that at the end I just get E0, right? I hope that this is clear, right?
Can you go over again what's
What is what?
Z?
Oh, Z is the basis that I'm using for my wave function. So so for example, if I have spin 1/2 the case that I described last week. So Z is the set of projections of the spins. If I have n spins, it's a vector of size n where each entry can be either 1 or plus or minus 1. Okay? So I think that last week I used this notation, or maybe I used this other notation. They're all equivalent, unfortunately, and sometimes I use them inconsistently. So the other one that I might have used is this one, sigma 1, 2, sigma 2, 0. Yeah, sorry. So these are all the equivalent notations for the same object. For spins, for if you had, I don't know, electrons or something else, these might be positions of your electrons. And, so this is quite general, but so the local energy is always defined. So the idea is that in all these calculations, you fix some canonical basis. So in this case, the basis of spins, or again, positions of electrons, occupation numbers, whatever you have. Yeah. But now, so you see why the local energy would be constant if, right? So I hope it's clear that you can see why the local energy is constant if psi is 0. So which means that also in this special case, so as soon as you get closer to the ground state, if you want, the dependence on Z, so on the configurations that you sample, if you want, in your Monte Carlo of this local energy will become smaller and smaller. So this, if you want, the closer you get to the ground state, the smaller will become the fluctuations of the local energy. Actually, we can be a bit more precise and compute the variance of the local energy, which I guess is what you wanted to know, right? So the variance of the local energy over this distribution P, which is psi square again. So so this one I will not do the calculation explicitly, but I invite you to do that. You can show that it is exactly equal to the fluctuations. So this is non-trivial, by the way, but you can show that this is exactly equal to the fluctuations of the Hamiltonian. Okay, so the expected value of H squared minus the expected value of H squared.
The Hamiltonian here, this is not the matrix.
This is the Hamiltonian or which that defines the local energy, if you want. Yeah, the same H that I have here. So it's the operator I'm trying to diagonalize. Right?
So what's the relation with the two brackets?
Oh, okay, yeah, yeah. Yes, sorry, you're right. Yeah, okay, sorry. Yeah, okay. Let me be explicit. So it's the expected value over psi of h squared psi divided. I mean, so that was the bracket, okay? Minus the expected value of the Hamiltonian over psi. So the quantum expected value, if you want square, this as a square. Okay. Right. So I mean, in short, I wrote it as the. So, but you see that now we've connected not only the first moment of the local energy. So the first moment, so the expected value of the local energy over P, as I've shown you last time, is exactly equal to psi h psi, right? Right. So this is what we showed last time. Now, what I'm telling you, I'm not proving it, but it's an exercise that also the second moment of the local energy is connected to the second moment of the Hamiltonian expected value. Okay? Unfortunately, this is not true for higher moments. So this is very special for the first and the second. The third is not equal to and the fourth. But the reason why I'm mentioning this again is because you see that the fluctuations, the statistical fluctuations, which is what you have on the left, of the local energy are related to the variance of the Hamiltonian. But again, if psi is an eigenstate, you see that h squared over psi will give you E0 squared, so a constant, right? And this will give me also E0 then squared. So you see that I have 0, the variance will be exactly 0. So that's why we call this the zero variance principle, because as soon as you get closer to the ground state, the smaller the variance that you will have on the estimates of the energy, and the smaller the variance you can show on the gradients of the energy, which is also beautiful, because you don't need to do dirty things that like you do in reinforcement learning, where you have to remove, I don't know if you're familiar with that, but you have to remove baselines and other things. So here the baseline is automatic in a sense, because the fluctuations automatically get reduced when you approach the ground state. Okay. Great. So right. So this is indeed very. So thank you for the questions, because I wasn't planning to mention this, but it's a very important point. You might have seen also in the experiments, numerical experiments, that when you approach the ground state, the fluctuations become smaller. I don't know if you noticed that, but you can maybe go back and try to see that. Now, going back to the goal for today, which is learning from experiments. So let's set up the problem here. So of course, learning from experiments is a very broad task and very broad set of problems. So I will not tell you everything. So for example, I don't know if you've seen how to predict or try to predict phase transitions. Maybe, I don't know if you've seen examples of that, maybe not a problem. But that's one example of what you might learn from an experiment. It's not what I'm going to do today. What I'm trying to do today instead is to be in a setup where I imagine that my experimentalist friends have prepared some quantum state. Okay, so they prepare some state phi, or in their experiment. Okay, so this is an experimentally prepared state. Could be a state of spins, for example, or even a quantum computer. You know, that's a quantum state that you can have access to through the cloud. Okay, I don't know if you're have done that, but it's fun. So you have this quantum state. However, I mean, you don't trust your experimentalist friends because they're experimentalists, right? So you want to actually make sure that what they prepared is actually what you think they prepared. Okay. So if you want, our task here will be to somehow certify that the state being prepared by, again, a quantum computer or a cold atom experiment, anything that contains a wave function, essentially, a pure wave function. So I'm concentrating to the case of pure states for simplicity. Then this can be is what they thought and prepared. Okay, so now what can you do on these quantum experiments? So what kind of information can we extract out of these experiments? Well, what you can do in a typical experiment is that you can, for example, measure. Yes, just I'm trying to use a notation that then will not confuse you later on, but okay. So what you can try to do is that you can perform projective measurements. Okay, projective measurements. Now, I don't want to go into the details of the measurement problem and the measurement process in quantum physics, because otherwise we will not see the end of the day. But let's say projective measurement just means, for example, if you have your spins, so you prepare your quantum state and then you read out the value of these spins. Okay, so whenever you measure the wave function, you know that it collapses to some eigenstate of the operator that you are measuring. This is in a nutshell how quantum measurements work. And in this case will mean that, for example, so imagine that I prepare the state, I measure it. Let's say that this state is two-dimensional, okay? I have a two-dimensional set of spins, why not? So, and they are on a lattice, or I mean on a discrete grid, okay? And then, I mean, I just read out the value of the spins. So for example, the first one might be up, so I draw it in red, the second one down, right? So on, so some of them will be, I don't know, some of them up, some of them down, I don't know. So there will be some distribution for this. So this will be the result of my first measurement, okay? So in other words, I will indicate this with Z1 like this. Again, Z now is the vector of all plus or minus one, and I've done the first measurement, so that's why I have this other index Z1, right? However, as you know, quantum mechanics is non-deterministic in the sense that if I redo the same experiment, so if I prepare the same exact state, and then I measure again, I will find that the spins are not exactly in general in the same states that they were before, okay? So I will obtain then another sample where my spins now can be, for example, this one might be down, 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 like this, and then the others are up, okay? So there is now some variations compared to Z1, okay? So and I can do this a lot of times. So let's say that I can do this m times. So I can ask my experimentalist friend or even myself, if I go on IBM Qiskit and run the quantum computer, for those of you who know how to do that, then I can perform these measurements and I get out of these strings, plus minus one, okay? M of them. Now, we know from, again, the axioms of quantum mechanics that the probability of observing a certain string is given by the Born's rule. So we know that this probability, let me call this Q of Z, is given, so which is the probability of observing a certain, so if you want, the probability of observing a certain Z, okay? So this is given by Born's rule. So assuming now that phi is normalized because nature normalizes, or let's say tends to normalize states. Now this will be given by just the amplitude squared of phi in this basis that I'm taking. Yes.
Is this conditioned on a state? This Q of Z?
Q of Z, yeah, phi is the state that I'm trying to, that the experimentalist has prepared. So the experiments that I'm prepared here is that, yes, so this is a Q, yeah, depends on phi, yes. But again, the experiments that, so these are destructive measurements. So which means that every time you perform a measurement, you have to throw out the experiment and then prepare another one that that constructs again the state phi, measure again, and then you have to do it a lot of times. Okay? So I'm not really talking about consecutive measurements, because if you measure it again, this you will find exactly the same distribution of z, right? Because that's an eigenstate of z. So when you measure it, you find again itself. So I'm really thinking about preparation, measurement, okay? Not a sequence of measurement on the same state. I hope this is clear. Okay. Good. Okay, so, but the probability of observing these strings is phi squared, right? And now our goal, if you want, the thing that we would like to do with machine learning, or in general, not necessarily with machine learning. So the goal is to perform what is known as state reconstruction. So state reconstruction means that I would like to find, if you want, a state. Let me call this state psi. Okay. That is as close as possible to my state, to the state phi that the experimentalist has prepared. Okay, so just to be clear, so this is the experimental state, and I have access to this experimental state only through this projective measurement. So it's given, if you want, implicitly. I cannot compute the amplitudes of phi explicitly. I can just observe what a result, the outcome of a measurement. Okay? This is the main limitation, if you want, in this setting. And this instead is some, if you want, variational representation of the state. Okay, so if you want, I can say now that this psi depends parametrically on some thetas. So now the goal will be to find this theta such that, I mean, again, these two states, so this psi theta and the this experimental state phi are as close as possible. We have to see, we have to define what as close as possible means, but you understand what we are trying to do here. So I'm trying to find an explicit parameterization or an explicit state that I can work with now on my classical computer of the state that the experimentalist is giving me and that I can access only through measurements. Okay, so this is what we can call quantum state reconstruction. And the idea is that if I've done that, after I've done this reconstruction, then on my state psi, I can measure whatever I want. I can measure any property, and then I can do a really systematic screening of all the properties that I want to make sure my experimental state satisfies. And there are some cases where there are properties that are not easy to access experimentally, but that instead we can measure in Monte Carlo-like simulation. Okay, so this is also one of the reasons why I want this. Okay, now the question is, is there some sort of variational principle or something that we can use in this case, right? Because once more, if you want, we are in a case where using the standard variational principle, so minimizing the energy, it does not really apply to this situation because we don't have a Hamiltonian, we just have a state, right? So we have a state that the experimentalist has given us. So there's not an intrinsic Hamiltonian associated with this state, not necessarily. What we can do though is that we can think about this problem from the point of view of probabilities. And in general, I mean, if I have my, again, my experimentally accessible, my experimental distribution of these strings, that is Q of Z, as I was discussing before, you can also think that the model we are trying to fit, if you want, to these experiments. We'll also have an associated Born distribution, which is actually the same that we've considered in Monte Carlo sampling. And this is just, z psi squared, okay? So if you want, I mean, we can also put a normalization if you think that your state you're working with is in general not normalized, okay? So you see that I have two probability distributions. So one that corresponds to the true quantum state, the one on the experiment, and the other one, which is the model quantum distribution. So what I can do is that I can do unsupervised learning, so standard unsupervised learning from the data set that the experimentalist has given me. So have you seen unsupervised learning in this school? Yes.
You don't actually have access to the probability, right? You only have access
To the samples, yes, perfect, yes, yes. So we'll see that this is not a problem. So indeed, so we know that this probability Q exists. It's a well-defined theoretical concept, but we don't have access to, we cannot query it to know what is Q of Z for a given Z. That's the problem. Yeah.
But you know that these are samples according.
Exactly, yes, yes. So, but you know that now, if we can, this is a standard problem in a sense in unsupervised machine learning. Because typically, yeah, indeed, you have images of people, but you don't know what is the probability of people, right? So you just have samples from that probability. So it's exactly the same situation here. So what we can do then is that in this context, we can define, for example, we can do maximum likelihood optimization essentially to find the thetas. And it's useful to, for example, reason in terms of this KL divergence that hopefully you've seen. So this relative entropy between the distribution P and the distribution Q. So this is defined as the, for example, P given Q. So this is defined as the sum over Z of Q, so my unknown distribution, times the difference of the logarithm of Q of Z minus the log of P of Z. Okay. So this is really the relative entropy. And you know that in this case, so if, for example, P is equal to Q, so you see immediately from this formula that these factors will cancel and this is going to be equal to 0, right? So if the two distributions are identical, then this DKL is equal to 0. And in general, it's not hard to show that the DKL is also positive or equal to 0. So which means that we can minimize it as a function of the parameters in P, okay? So now this will be an object that depends on the thetas and that has a minimum at 0. So we can just minimize it, right? So this will be, if you want now, my variational principle. It's not on the edge, it's on the statistical distance between these two samples, these two distributions. Okay. So this is my loss function, if you want, that I can minimize. And the beautiful thing about the KL, or if you want, just the maximum likelihood estimator that has exactly the same minimum of the KL, if you prefer that, is that you can, the gradients of the KL divergence, so Kullback-Leibler divergence, KL are the initials of these two people, can be written in a very nice closed form. So I'm not deriving it. Okay. If you want, we can derive it, but okay. So let's say the derivative with respect to parameter theta L, let's say, of this DKL, so this distance that again depends on the parameters theta. Okay? So you can show that this is written is equal to the difference of two contributions. So the first contribution is the gradient with respect to theta L of the logarithm of the right? So of the logarithm of the unknown. So okay, so let's. Okay, so let's write this in this way. So we can write this as fz divided by the normalization. Okay. Because I've told you that typically we don't know the normalization of the state that I'm trying to normalize, that I'm trying to represent. So what I do is that I represent with some neural network, okay, the unnormalized amplitudes. So let me call f of z these unnormalized amplitudes and psi the unknown normalization that is. Okay. So now, if with this definition, which is the usual that we used also last week, then we have that the logarithm, so the gradients are the logarithm of f of z, okay, over the probability distribution p, so the one that is given by my model, okay, minus a second term, which is the derivative with respect to parameter theta L of the logarithm of f of z, but now this average is taken over the samples that are given by the experiment. Okay. So these are the gradients of the KL divergence. So these two terms, again, you should do the calculations and make sure that you follow the right steps. But so they, for example, this one or this one, yeah, should come from the normalization from the gradients of the normalization of your probability distribution. And this is just, in a sense, the signal that you get from the maximum likelihood. Okay, so if the distribution is not normalized, you will also have these terms. These other term here, if you want. Okay? Now, so you see that, however, the interpretation of this is quite nice, because the expected value now the gradient can be computed with two averages. So the first one is performed over data that is generated from my model. Okay, so what it means that at each step of gradient descent, I generate data from my model P. So from the square of my wave function, like in TMC, right? So like in conventional Monte Carlo. And then on these samples, instead of averaging it and compute the local energy, I will use to average it and compute the expected value of the log of my model, right? So this is again something that I can do because I know how to compute this is typical. Actually, the log of the psi is parameterized like a neural network. So this is just the gradient of a neural network. Yes.
Again, like, yeah, I get the point of the exercise, but like in practice, we would just like, you would not do this calculation ourselves, right? Like you would just define the loss and then.
You can try to do that, but you get the wrong result because the point is that you don't know, you cannot write the explicit loss because you don't know the normalization. So you have to be careful with that.
So in some sense, we're just normalizing over all the coefficients, right? Like,
sure, but to compute the normalization, you need to sum 2 to the n possible values. So you don't want to do that.
okay.
So if you could do that explicitly, then sure, you just do AD and you go through that. However, or if your state is normalized, indeed, this term will not be here, and you only have this one, and and this okay. You can get it just by standard ED, but you have to be careful when the distribution is not normalized, because otherwise you don't get this term.
How do you sample from your model in this case?
Yeah, so it's exactly the same story as we discussed last week. So you see that P, so the distribution I have to sample from, is psi square. So we can use Markov chain or this exact sampling if we have this autoregressive structure. It's exactly the same as last week. And then yeah, so the other term that you can see here is that is the mean over Q. So these Q samples now are fixed, just what the experimentalist has given you. But you see that indeed, if now P and Q are identical, the gradient is 0, right? Because you see that these two will give exactly the same average, and you will be at the minimum or the local minimum at least of this loss. Okay. So yeah.
Is this related to score matching? If you know what that is?
this is just maximum likelihood estimation. So I define the probability of my samples given the model, and then I maximize this or equivalently minimize the log minus the log of this probability. Yeah.
Yes.
Let's say maximum likelihood is as old as Fisher, which is 1913. So that's why I don't like referring to more modern things, because it's really an old topic in statistical, in statistics, right? Now the other thing, yeah. So actually, maybe it's worth mentioning that the derivatives of the log of f of z, just to connect to what you wrote maybe last week, these are what I called the O's. I don't know if you remember, but at some point I was discussing these O's when discussing the gradient of the energy. Right? Maybe I can go back actually to the slide that I had here, or maybe not. But so I don't know if you remember, but when yeah, you see here, right? So you see when we discussed the gradients of the energy. So this was the gradient of the energy. There was this O appearing, right? And this O is exactly the same quantity that I'm now using also for this other problem. So it's just the gradient of the log of the output of your neural network, typically, because I parameterize the log of the wave function with the neural network, typically. Okay. Great. So everything is computable efficiently, provided again that you are able to sample, and the strategy is very nice. I mean, at each step you regenerate sample from the network, measure the gradients, regenerate, measure, back and forth until you converge to something that minimizes decay. Okay. However, there is something that I have carefully hidden from you at this point, which is the fact that wave functions are not probabilities, but they have a phase, right? So you can see immediately that here there is a problem, because if I do this, so I will find a psi, a model psi if you want, and now it depends on the thetas, whose square, so psi square now will match phi square. Okay, but what about the sign or the phase of phi? So there's no way that I can reconstruct the phase of phi from these measurements, because there's an arbitrary phase that it's just not there in the when I sample from experimentally from phi.
I see. So you're just saying like we can estimate the magnitude, but we can't estimate.
Exactly. Yeah. So in this strategy that I just described, we can only estimate the magnitude of this probability of the wave function amplitudes, but not their phase, again, because they are complex, right? So how can we do that then? So how can we estimate also the phases?
We must change our Q, right? The problem is the Q is like some squared terms.
So that's why this problem is often called also tomography, because you want to look at your patient your wave function not only in one direction but in other directions, so that you can reconstruct the 3D image, right, of your patient. And so that's why sometimes we call this tomography. So this application of so indeed the idea is that you want to measure. So instead of measuring only in one basis, so this is Z basis. So we want to measure in more basis, measurements in more basis. Okay, so maybe I will give you just a small example so that you can get an intuition why this works and what this is about. But let's consider, for example, I will consider a single spin example so that we are on the same page. So for a single spin, imagine now that my experimental state is this one. So phi, so now it's just a vector of size 2, right? And then I can imagine that it has some phi up, right? Yeah, so sorry, let me just call these coefficients, so C up and C down. Okay, so this is just a, a two-dimensional now wave function. We discussed this at the beginning of the lectures. Okay, and now I make the assumption, for example, that the first coefficient is real. Okay, and the second one, it has a real component, if you want, times a phase e to the I gamma. Okay. So you see, again, as I was mentioning, that the probability amplitude, so if you want my Q of Z, now in this basis will be just the square of this coefficient. So this will give me, for example, CR squared and the square of the other one, which is CR, sorry, down. I don't know why I wrote it up here. Okay, so these are in general two different numbers and square. So you see that there is absolutely no information on phi. Yes?
Okay. This kind of, so this is the modeling choice in your.
No. I'm assuming that so you can describe an arbitrary qubit state, so a single spin state with only 3 parameters, right? Because the fourth is redundant, 3 real parameters. So 1, 2, and 3 because of the normalization. Yeah. So this is the box sphere represent. I mean, that you need only 3 parameters. So these are the 3 parameters I'm choosing. It's arbitrary. And I'm picking an arbitrary phase difference. So I'm just picking arbitrary that the first coefficient has 0 phase and the second one has some phase. But this phase difference is arbitrary because of the global normalization of the state. Okay.
So what you care about is only that there is a
the total phase is arbitrary, not the phase differences. Yeah.
You're just changing a basis so that the first one is.
Yes, I can just pick the coefficients in a way that the first, this first thing is real and the other one is complex for this single qubit case because of the normalization and the freedom in the choice of the global phase of the state. Great. Now, so my probability again, Q of Z contains nothing about gamma, and you can see it already. This was already clear from before. So what I can do though is that instead of measuring in the Z basis, which is what I'm doing, because now I'm assuming that these coefficients are in Z basis, I can measure in the X basis. Okay. So instead of measuring the spin in the Z direction, I can use a Stern and Garlock or whatever apparatus you have to rotate, if you want, my system and measure in the X direction. So how do I do that? Well, mathematically, this is a basis change, if you want, in my state vector, in my vector phi. And this is realized by an operator, H, which is not the Hamiltonian, but unfortunately it has the same form, which is the Hadamard gate. This is known as the Hadamard. Okay, so this is written as a 2x2 matrix. So this is just the basis transformation. So it's a unitary, if you want, operation, and it takes this form. So this is known as the Hadamard matrix or the Hadamard gate. Doesn't matter. Okay. So this is a base transformation that transforms a state which is defined in the Z basis into a state that is now defined in the X basis. So that when I measure in the X basis, I will get coefficient from this transformed state squared. I mean, the measurements will be sampled from this. So just to see what happens then is that my phi, my state, if you want now in my X basis, is just given by the application of the Hadamard to the my initial state, if you want, in the state in the Z basis. Okay, maybe I will just be explicit and put a Z here. Okay, now we can do the calculation if you want. Right. So now we will have that this phi x be equal to 1 square root of 2, 1, 1, 1 minus 1, and then I will have this C down real, sorry, C up real, C down real e to the I gamma. Okay, and then you see that this is going to be 1 over square root of 2, and then my coefficients, if you want, in this new basis will be C up real plus C down real e to the I gamma for the first component, and the second one will be C up real minus C down real e to the I gamma. Okay. So this is the wave function in the new basis. So now when I measure in this new basis, I will measure from a new, if you want, probability that I can call Q of X, QX. And now, still, the eigenvalues of the sigma X operators are still plus or minus 1. So that's why I'm calling them still Z, right? Because I can, when I measure the polymetrics, so if you want my spin in the X direction, I can still get plus or minus 1. So Z are just the eigenvalues of this operator. So hopefully you don't get confused by that. But I'm just getting plus or minus 1 again, but with a different probability. And this probability is just the square of what I just wrote here. So it will be 1 over 2. And then I will have, C up R plus C down R e to the I gamma squared. And then I will have C up R minus C down R e to the I gamma squared. Okay. Now I have to do a little bit of algebra. Okay, so you see that in the first case, so the real part of this would be C down R plus, C. So C up R plus C down R, the cosine of gamma. So this squared, so this is the real part, if you want, of the first expression, plus the square of the imaginary part, which is nothing but C down R times this sin gamma, everything squared. Okay, so this is elementary trigonometry, but okay, let's do it. So CR up minus C down R cos gamma squared, and then here we'll have C, I don't know, C down R sin gamma squared. Then I have a factor 1 and 1 over 2. All right, I mean, I guess we can further simplify this. Which I don't want to do the calculation because it's boring. Okay, maybe let's do it because so I get 1/2, and then I get C up R squared then I get the cross product. Okay. So you see here I have C down R squared cos gamma squared, and then here it will have C down R squared sin squared gamma, but cos squared gamma plus sin squared gamma is 1. So I'm left with C down R squared, and then I have the cross product, which is plus twice C up R C down R, and then I have the cosine of gamma. Okay. So and down here, the only difference would be that I will have a minus. Okay. Anyways, so this is the beauty of interference, because now you see that this probability will depend on explicitly on gamma. So if we take, for example, the extreme case where I don't know, gamma is equal to pi over 2, so you see that so this term here will be exactly equal to 0, and you will have that instead this other term will give you a contribute. Sorry, so let's say simple case, gamma is equal to 0. Okay, so then this probability will be greater than this one. Okay, so you see that you can create an imbalance in measuring up or down more often than and this will depend on gamma. So this will contain information. So this is just a simple example, but just to tell you that this contains information about gamma. So now we can hope to reconstruct also gamma. Yes.
So when we make the second measurement, again, we have to reconstruct the state.
Yes. So the idea here is that what you do, so you start with your state phi. Okay. Now you want to measure in the x basis. So what you do is that you apply this unitary h. Experimental, you can do that. On a quantum computer, you can do that. And then you measure in this, you measure again this state phi, you measure the state phi, and then you collect this set of measurements in this basis now. And you will do this for as many bases as you want, or as many bases as accessible on your quantum computer. Typically, of course, you don't want to do infinitely many bases, but sometimes one good choice is to just pick random bases. For example, you might measure the first spin in the x basis, the second one in the y, the third in the, you can go crazy and just pick random measurement basis for each spin, and this will give you information, non-trivial information. All of these bases will give information about the phase, if you want, of your coefficients.
So if we have n particles, I think you need to make n-1 bases.
Right? No, because the coefficients are 2 to the n, right? Remember, so you want to determine 2 to the n phases. I mean, -1, but okay, fine. So in principle, you need exponentially many bases, but in practice, unless your state is very ill-conditioned or has some weird properties, for physical states, for example, a few bases are enough to reconstruct the phase. Okay. But sorry, you had a question.
Well, maybe you just answered the explanation. But this has to happen before I get the.
Yeah, so let me tell you maybe what is the exact protocol. So this was just to give you a motivation why you need more bases. Now I hope that this is clear. But now what we do is that we minimize the KL in all bases that I have chosen to pick, right? So what this means is that, so if you want, each of these bases that are picked will define some probability QB. So now B is one of the many possible bases that I've picked. And this probability density is given by just some unitary matrix applied on my state phi. So U, if you want, is just the unit that transforms from one basis to the other that is known, and you can apply experimentally. So there's nothing problematic there. So this is again theoretically, these are theoretically the QBs that you don't have access to directly, but only through experiments. But then you can define once more a KL divergence that will depend, of course, on the parameters of your model, just by summing not only over the Z, but also on the basis. Okay, so I will sum now over the B's, the possible bases that are picked, and over the Z of what? Of QB of Z. Okay, so if you want now, I minimize the total KL, the sum of all the KL divergences in all bases. So I try to minimize the KL divergence in each of these bases. So I will now have QB of Z plus, so minus the log of PB. Okay, so this is maybe the only object that I have not told you about, but essentially PB, as you can imagine, is just the rotated, if you want, transformed model probability. So that is obtained exactly in the same way. So I just apply this unitary matrix on my model psi, right? And I take the square. With some normalization that actually should be independent of the base, because this is a unitary transformation. Okay. So this means in practice that you take your wave function, you apply this linear transformation that is this U, right? And you can do that efficiently if this U has some special properties, but I don't want to enter too much into the details. Essentially, if it acts only on a few qubits or a few spins, few means not polynomially many, but constant. Okay. Then, if you can do that, you can construct the explicit value of PBZ, of the unnormalized PBZ, and then you have all the ingredients that you need to minimize this scale, because then you can take the gradients. You can do so. Then here, for example, it's especially useful to use automatic differentiation because you have a linear combinations of your models that are given by this UB. You don't want to do the gradients by hand, so that's especially useful when you use JAX or whatever. So if you want more details of this, they are of course already in the lecture notes that I linked in the last in the first lecture. Otherwise, this is described in a work that we did some time ago. So this is Nature Physics 14447, okay, 2080. Okay, great. So this is all I wanted to tell you about experimentally driven. So this is really limited, as you can imagine, subset of things that you can do with your experiments. But it was just to give you an idea of that connects nicely, I believe, with what we've seen last week. Right. So I think that the program was to have maybe another half an hour, if I remember correctly, more or less. No? Yeah. So what I wanted to do, so first of all, if you have questions, don't hesitate to ask, because it's a good time. Yeah.
Yeah. Just one question, like the expectation, like this, whatever energy that we compute is independent of the phase, right?
Independent of the phase.
Or no? Because I thought it only depends on the probabilities, like the magnitudes.
No,
for example,
sorry, say that again. I did not
for example, like
understand.
the energy that we computed.
The energy that we compute depends on the phase, yes, because the local energy. Okay, let me just take another page with Scratch for questions. So the local energy is this one, right? So, okay. And we've seen last week that, I mean, okay, now we can rewrite these if you want explicitly as the matrix elements of the Hamiltonian divided by psi of z prime over psi of z, right? So you see that in this expression, we have psi, not psi squared. So here, the phase of psi truly matters, even though this is average over psi squared, but the phase enters here in the local energy estimator.
So in some sense, like we're getting information about the magnitudes, like we're getting like there is still like 2 to the power n coefficients, right? We are getting information about that from just one experiment, like the magnitudes.
Yes.
But for the phases, we have to do like so many more experiments, right? Like for
You have to do many more experiments for the data driven. Yeah, you have to do many more experiments because the phase is more challenging. There's nothing. Unfortunately, there's no way out. That's the nature of quantum mechanics. Yeah. Sorry about this bad news, but so what I will do is that I will try to set up now my computer because I wanted to share a presentation that unfortunately I don't have on the iPad. Because in this last half an hour or so, I don't know, we'll see. I will give you maybe just an idea of what are the applications of these techniques, because I've talked a lot about techniques, but I didn't tell you if they work or not. Right? So I wasted your time or something. Hopefully not. So let's see if I manage to do this. Okay, so to do this, I will just need to know the Wi-Fi password.
It's Simon Zenley.
Okay.
This can be also done in a statistical sense if you have just an energy. But why do people score matching? Yeah, but yeah, but that will also minimize that payout. So why do people go for score matching and not doing this in machine learning?
This is like a variation. This is very similar to like any variation.
This one.
Yeah, minimizing the key and that was.
Yeah, but why don't people do?
I mean, in some cases they work well, some cases they don't. This is how it's. This more.
You know, the energy. When you don't have the gradient of the energy, like you only see some.
Yeah, but here you only have
Okay,
also.
so I think we are kind of back online more or less.
No, yeah, that alternative.
I just wonder if you could do this using score matching as well, and then maybe get better as well.
That's your
Same
summer
payout.
run.
Yeah.
Like the whole.
Yeah, I mean, you have to have some notion of what it means to add noise. Maybe noise is all these code base. Models of regular noise.
All right. Okay, can you see anything? Yes. So I updated also from home or wherever you are. You can see it. Maybe it's clear, the audio is clear like this. Okay, great. So, yeah, so I just wanted to give you an overview of the basic applications that we do. This is really not a comprehensive list of applications, but just to give you an idea. Okay. So, one problem that we've been studying a lot, one of the ground state problems we've been studying a lot, I mean, especially because this is an interesting benchmark for many new solvers of ground state problems, are what we call frustrated spins. These are the hardest easy problem you can think of in quantum, in condensed matter, if you want. So these are two-dimensional spins that are set on a square lattice. Okay, so you have spin 1/2 as before on a square lattice, and then your Hamiltonian contains interactions among spins on that are nearest neighbors. So this one and this one would interact through this J1 term, and then this J2 term, which is on the diagonal. Okay, so why am I saying that this is a hard model? Because when J2 is finite, we don't know how to solve this with any other technique, with any numerical technique, or analytically, it's even worse. Okay, so instead, when J2 is 0, we have a quantum Monte Carlo, which is a series of other approaches that I really didn't discuss, but you can look it up. That allows you to study this. But when J2 is finite, we have what is known as the sign problem, which is an issue that does not, essentially makes things complicated for these Monte Carlo techniques, these other Monte Carlo techniques that cannot be used to solve the model exactly. Now, so the issue we need now from the physics perspective, for example, is whether when J2 is comparable to J1, there is a phase that we call the spin liquid, which is a sort of disordered phase that intervenes other cases where instead my spins are well aligned either in this antiferromagnetic order, so this up, down, right? I used the same colors by chance of the last slides on the iPad, or this striped columnar phase. So this is the kind of questions we want to understand. So starting from the first work that, that we did in 2016, we already concentrated on this model in the limit of J2 equal to 0. So this is what we call the Heisenberg model. So this is nice because again, we know how to solve that. So we have benchmarks that are pretty precise for this limit, so we can already test our variational states. So in this case, what you can see here was 10 by 10 clusters of 100 spins. This was the error on the energy, and here I was increasing alpha, so the size of the neural network that I was using. That in this specific case was just an RBM, so a very simple one layer, if you want, or deep shallow neural network. And so the only thing that you can tune there essentially was just the width of the neural network, and this is alpha. Okay, so alpha is proportional to the width of the neural network. You can see that by increasing alpha, you could improve the accuracy, so this error goes down. Okay, and we could also improve some of the results at the time that were some other variational states. But by going a bit deeper, so 2019, we found out how to work with convolutional neural networks a bit more efficiently than what we were using. So again, it's not because we don't know how to use TensorFlow or anything. It's because in these applications, these are considerably more challenging from the numerical perspective, since you need to sample from your models, and you have a back and forth, so you just don't have only external data, automatic differentiation, and minimize. So it's much more complicated. And also we needed complex numbers. So you might think, okay, TensorFlow maybe has complex numbers. PyTorch didn't have them or didn't even exist when we started. Now most common frameworks do have complex numbers, also because we back them for quite some time. And they work nicely with complex numbers. I would argue that JAX is the one that works the best with complex numbers, and that's why we use it. But again, that's why, you know, it took us some time to use this deeper network, because there was not really a good infrastructure to use that. Anyways, just historical background of this. So, because you might say, why don't you use a transformer with 200 layers? I don't know, because, you know, it's not so easy to do. And then you see that by using, you know, like I think this was a 3 or 4 layers combinate, nothing crazy. You can improve already on this RBM. So I put it here because this has the same number of parameters of this RBM that was here. So you see that going deeper rather than wider as an effect, which is nice. And then, I mean, as I was mentioning already last time, we discovered this family of quantum states that are automatically normalized, that have this, that is what we call autoregressive quantum states. Okay, and these are nice because they are allowed to do exact sampling, so they are much nicer to work with, also with standard, if you want, settings. And with this, I mean, okay, now we are a bit more serious. We can use minimum parameters finally, which, you know, it's not exactly state of the art in terms of what you can do with a language model, but, you know, it's still more than a few thousand that we were doing here. And you see that you see an effect because the error is off scale. I mean, I put it here exactly because I wanted to show that this is off scale compared to the first. And, you know, an error of 10 to the minus 5 is essentially extremely good because this is the error on the energy. So as a rough estimate, you can think that then the error on observables will be the square root of this. So if you have 10 to the minus 5, you would have 2.5, I don't know, something like that on the a few percent error like on observables, which typically is not too bad, and it's actually pretty accurate, obviously. Instead, if you have a percent error on the energy, the observables can do whatever they like, essentially. You have order 1, more or less, error, okay? Now, when we increase the frustration, so when we call frustration the fact that we introduce this J2 class value. So in 2019, using this COMNET, again, our first attempts with COMNETs, we managed to improve most of the existing variational results. So you can see here, these are the energy differences so between our CNN and some other existing methods. So you see that if these points are in this upper part of this diagram, means that our energies are lower, which means that we have a better approximation of the ground state. If they are here, it means that these other methods are better, so they have a lower, if you want, estimates of the energy. And you can see that, you know, for a first application, this was not too bad because we were improving on everything in all the phase diagram, but for this point around 0.5, where you can see that this DMRG approach has had a better energy still at this point in time.
So this DMRG approach is not like neural network.
DMRG is this tensor network method that is especially suitable for 1D applications, but it can also be used, it's more expensive, but you can also use it in 2D. And so typically it has a cost which is exponential in the size of the y direction, if you want, in your two-dimensional system. You can do it up to 10, 12, and then especially for systems, and then for spin system, you can go to these large values, but then you lose some accuracy. But you can see that on 10, it's still very, very precise, very competitive. But, okay, I mean, I can tell you, for example, that we believe that around 0.5, for example, one of the reasons why neural networks have issues or, I mean, are not so effective as in other cases, because they need more samples to learn the states. This is what is shown in this paper. I will not go into the details, but essentially they show that if you are close to this disorder, so frustrated is also synonym often of disordered, so states, you need a lot more samples because they're more entropic. So you need to see more samples to learn them. So that's why also they are harder to learn than these ordered phases that instead are they are easier, right? So it's easier if you look at a crystal rather than at a gas that instead is completely all over the place. But this is to say that in 2020, the situation changed because people realized how to use symmetries more efficiently. You can have a look at this paper, and so this is this 0.5 point that was a bit infamous for the neural network because it was the one that was still not the most accurate. But at this point, so this was our result, CNN actually. This was what we got in the last in the paper that I showed, that the DMRG was lower. Okay, and this is the best neural network estimates. It's actually the best the best variational estimate overall on this model. So at this point in time, you know, this was actually 2 years ago. Neural networks are state of the art on this frustrated problem. Okay, this is true also for other problem models. I'm just showing you this because again, this is the simplest hard problem you want to solve in 2D. And there is, and this is done with essentially an RBM. This is fun because this is an RBM with some small physical insight in the prior. So essentially, what they do is that they multiply the RBM with a mean field wave function that has some prior information on the physics, but it's really a simple mean field wave function. This PP, and you see that just by multiplying it with a correcting factor, if you want, that is more general and has the form of an RBM, this allows you to improve significantly over all the other methods. So this is also a hint to the fact that if you can combine some prior knowledge that typically can come from some physical insight on the problem with the generality of neural networks, you can essentially do a lot better than just starting with neural networks. Even though I claim that now we can do it also without putting the physical insight, but with a deeper network. But okay, that's a secondary point. So something that was discussed, I guess, by Javier was how we do fermions, right? So he told you already about this, but so I don't want to go too much into the details. But so essentially, what we do is this one possibility is to do this Jordan-Wigner mapping. Where you transform fermions in fermionic operators into spins. So fermions are described by these fermionic operators that satisfy these anti-commutation properties. However, you can transform spin fermionic operator C into spin operators, so sigma plus, sigma minus, through these Jordan-Miller strings. Okay, this is mostly for the physicists I'm talking to, because this would require a lot of preparatory material if you wanted to understand it in detail. But in essence, if we have fermions, and again, electrons, for example, are fermions, they are not just simple spins, so they really have this fermionic property that when you exchange them, you get the plus, you have to have a minus sign in the wave function. So then if you want to do electrons, so for example, that are relevant for molecules, then the one idea is to transform these fermions into spins, spin 1/2, and then use the same techniques that we just used so far to study other spin properties. Okay. And then, I mean, we've done this for a few molecules. So this is, for example, the energy that you get when you try to dissociate two molecules, a molecule that is a diatomic molecule. For example, when you pull apart two carbon atoms, then you will see that the energy will increase if you try to put them together. I mean, if you try to push them too much together, because of the Coulomb repulsion, essentially your energy will go up, and this is what you see here at distance that approaches 0. And then there is a minimum, there's an optimum, if you want, in the energy, the lowest energy, that corresponds to the equilibrium distance between these two atoms, right? This is what this curve shows you. So there is a minimum energy that is what nature likes when it forms these diatomic molecules. And you can see again with our beloved RBMs that are easy enough to do calculations, we could already match in these small molecules, small basis sets for the experts, the results that you get with exact methods that are still doable in this case, that are in red. So these RBMs are in green, these FCI, full CI is in red, and you can see that we can match nicely and also better than some techniques that quantum chemists use, like these couple cluster methods. I don't know if there are chemists in the audience, but if not, you can look them up. Okay. There is an alternative approach that is not based on working with spins, right? So essentially discretizing your problem and working with this discrete set of operators. But it is something that has been done, proposed in this paper, and also in parallel by Google DeepMind, because Google DeepMind is also interested in our techniques. And the idea is to use instead the continuous space representations of your wave function. So in all we've done so far, I really didn't discuss the case where these Z variables could be actually continuous variables, like positions of your electrons, right? In this specific case, that would be the case at hand. So the positions of my electrons, but it's a very similar reasoning. So you just need to represent your wave function now in this continuous space with continuous inputs rather than binary inputs. However, in this representation, you have to be careful because your wave function must be antisymmetric. If you treat electrons, when you exchange two particles, you should pick a minus sign. And there are many ways to do that. You can look at them up in these two papers. And these are nice because they are already closer to the limit of the continuum, as we say, in the sense that they are directly comparable to experiments. Instead, when you work on the discrete, you have always to think that you have some discrete spacing elements, if you want, that you have to send to 0. So you have to do more simulations at different, on different basis sets, as we call them, and then extrapolate the limit where you take this thing to 0. Okay, so this is the main reason why sometimes these are better, but okay. So I don't know how much time I've left. I guess in the last 5 minutes, I will tell you about instead another family of applications, which is closer to the second part of the lectures last week, which was about simulating the dynamics of the quantum systems. And indeed, the dynamics of quantum systems is very closely related to what we call quantum circuits. So how many of you are familiar with quantum computing? So maybe before trying to understand if this is the right topic. So you're not, right? Okay, so maybe I will skip this part, or I will just flash the idea. But yeah, so I will just flash one result that we had with one student here at Columbia and also Flatiron. But essentially, so this graph that you can see here is a sequence of unitary operations. So each of these blocks, you can think of this as a unitary operation. This is what we call quantum circuits. So this is just a sequence of elementary unitary operations that you apply on some initial state. Right? So in a sense, it's a generalization of the time-dependent Schrödinger's equation. This is relevant for quantum computing. So we set our problem in trying to simulate this object and see if we can do better or worse than what you can do with an actual quantum computer. So a quantum computer does this thing by construction, because it's designed to realize these unitary operations, with your physical qubits, right? Instead, if we try to simulate this classically, we have to do some approximations. We have to do maybe a variational approximation. But can we do something that is comparably good or not? Okay. So, in general, this is a very open question. I would say it's not so clear that interesting quantum circuits cannot be simulated. But I mean, what we found is that, for example, if you take of the order of 54 qubits, which is what you have in this famous Google quantum processor that became very famous a couple of years ago because of this paper on so-called quantum supremacy, unfortunate name. So in that case, so what we showed is that if we run some specific quantum algorithm on this that is designed to run also on the machine, essentially what we can do is that we can predict the outcome of this result. I mean, I'm not going really into the details, with an accuracy that we believe for this depth, for example, p equals 4, so depth means how many gates you realize, is actually in this case better than what you can do on the actual machine at this point in time. So the reason is that the machine is noisy, because it cannot realize all the gates as in the ideal world. So every time you apply a gate on the machine, there is some error. So it's the same thing when you have a classical computer. There could be literally a cosmic ray passing by the room that will affect your bits in the hard drive or in the RAM, and this will destroy the calculation, right? And you know that there is error correction in classical computers that allows you to elevate and solve essentially this issue using redundant bits of information, right? So your information is protected because your single bit is encoded in many bits, right? So this is the principle of error correction. So something similar can be done also with quantum computers on qubits, using many qubits to encode one. But this is not done, not yet doable in a sense, because it requires some experimental advances that are not there yet. Okay, so these first machines can run only without error correction. So it would be your classical computer that suffers for all sorts of errors and the cosmic rays passing in the room. So it's clear that after a while it's unusable, right? Because you destroy completely your calculation. And in this context means that the depth of the circuit, so the number of gates that you can do, is also limited. You cannot go beyond a certain depth. And we estimate, we have good arguments to claim that for these specific circuits, instead, if we simulate the circuit classically, while we also do an error, because every time we apply a gate, we have to do some approximation, variational approximation. However, our error, we believe, is smaller than what you get in experiment for this kind of circuits. Okay? So, there's still this interplay, this, this game of catch with classical and quantum methods, but there's a lot of progress on both sides. And, there are still cases where classical computers are still under, I would claim 99.9% of cases where classical computers are better than quantum computers at this point in time. The situation might change. Who knows? Okay. Yeah, this was really the last thing I wanted to tell you, because otherwise I will just introduce more topics and it's not really worth. So I think it's best if you have questions, maybe you can ask them. Otherwise, again, I will be around, and also thank you for carefully listening to my lectures. If you have, if you want to go deeper in the material, just have a look at lecture notes. That's really an excellent place to start from. And yeah, thank you.
Thank you, Lynn, for being here. So this is the last lecture of this school. So thank you for coming.
Yeah, so my name is Yulen Gao, and I am currently a research fellow at Flatiron Institute, CCM, and my research is mostly focused on Bayesian statistics. So today, I would like to share a little bit on Bayesian model evaluation, comparison, and how to do model averaging in the hopefully in the more broad machine learning context. And so to start, I want to start by the question that why do we want to use Bayesian modeling at all? I believe in the past few days, we have already have a few classes on either Bayesian computation or on Bayesian modeling and non-parametric modeling. So maybe it's maybe some of the material have been overlapped. But nevertheless, I want to share the aspect like why do we want to what advantage of Bayesian modeling can provide even in the context of prediction. So it seems that the old saying is that, oh, we want to use statistics modeling if we care about estimation or if we care about causal effect, and if we only care about prediction, then we just use a deep neural net. Is that really the case? So here's a case study that we did a few years ago on apparently 2020, when we use this to predict 2020 election in the United States. And this is the joint work between Columbia Statistics and with the economics in the UK. So the goal is to predict election for the presidential election for 2020 between two candidates, which of course is a binary classification problem, right? But like the data is not like independent image or anything close to that. The data we have, the training data we have is like the polling from like different states and also national polling. But they are like time series data, so they're apparently not independent. And also it's dynamic because like the public opinion changed over time, which you can see is like the raw data here visualize like the polling for the two candidates over time. So it's dynamic. It's not independent. And also it's also hierarchical because we have like the polling results from different states. And it's also hierarchical because they come from different polling houses, and each polling company, they have like different target audience. So it's not IID. And also it's multi-scale because you have the polling in the national level, in the state level, even in the county level. And also you have other information that you want to incorporate, such as the GDP in the country, or like the economic growth in the country, and also like the past historical results in the past election, and which give you like, for example, the incumbent advantage of the current president. You also have, for example, the COVID cases during that time, because it's 2020. And then the question is, how do you want to incorporate all this information into your model? You can't really use a neural net, right? I don't even know, like, how do you even, like, it's not even, I don't know, like, how do you put a neural net to do this type of tasks like, I guess you can. So presumably you can have a like deep neural net, but then you have to have a very customized architecture of the neural net, which amounts to some probabilistic modeling. And also the basic, so that's why we want to use Bayesian modeling, because we can do this customized probabilistic modeling to incorporate all the information you have in the data. In addition, Bayesian modeling is appealing because it automatically converts uncertainty into a probability. So you can use probability to quantify uncertainty in your modeling and in your prediction. So what is a desired prediction in this particular context? We want the prediction to be dynamically updated, because every day we receive some new data from new public opinion surveys. So you want your model be able to update over time or even online. And you also want your prediction to be hierarchical. For example, you want a prediction for the national level voting result, but also maybe you only care about the election result in one particular state. So in the end, like, your prediction is not like a binary outcome for the election forecast. Your prediction should be for different state and even for different county. And also, when the new results gets revealed in a new over time in election day, you also want your prediction to be updated in other states. And also, your prediction is not one number, because it's not like, oh, you only want to predict who got the presidency election in the end. You also want to provide, like, for example, the interval prediction for what's the confidence interval of the final prediction, because maybe you are a gambling company and you are running some betting, so you do care about the interval, and also you care about the calibration, because even though it's just one prediction, but maybe this type of prediction can be used over time because you have a dynamic prediction. So you care about calibration. You want your if you predict that Biden wins by like 90% of chance, then you would hopefully wish that if you repeat this experiment 10 times, that your prediction would be correct for 9 times in average. And all of these features, of course, can be gained if you are running a Bayesian model, and if you do that correctly. And that's what we would wish to discuss today. So from the previous case study, it seems safe to draw the conclusion that there are some general challenges of modern statistics that can sometimes be unspoken. One is that big data is typically massive data. They are not like IID images that's like who just sit there and like await for your training. No, they're not IID data. They are not IID images. They are not pixels. They are massive data. They have like different scales. They have like different. They contain like other informations, and you don't know how to use that in the first place. And also, big data is almost always observational rather than design experiment. So if you want to draw causal effects from the data, you have to care about how the data is generated. Are they observational, or are they randomized experiments? And also, big data frequently uses available proxy rather than this direct measurement of the underlying construct of interest. for example, in the previous case study, the observed data we have is the polling from different states, which sometimes only represent the approval for the current president does not rather represent the voting tendency in the election day. Statistics always involve some extrapolation. And in particular, there are at least 3 extrapolations that we want to draw. One is from the observed sample to the population, and 2 is from the control group to the treated group, if you think about in the causal context. And 3 is from the observed measurement to the latent variable that you care about. You have to translate between these quantities. Yes?
What is kind of like the broad differences between these kind of extrapolations? Right? It seems like the settings are very different between these 3.
Oh, sure. I guess they often overlap. There's no clear classification, but it's more like a broad idea of why doing statistics is not the same as just like compute like sample average or just use a deep neural net that can solve anything, that can solve everything. So then why Bayesian models? It seems that the old saying is that, oh, we want to use Bayesian modeling because it returns some probability, and we want to use probability to quantify, to capture uncertainty. But like in some way, that's true because we start by a likelihood y given theta, which is the likelihood. You have some prior p theta, and then after you see the data y, you have the posterior inference. Then you integrate out your uncertainty using probability theory. Then you get your posterior inference on y, which is a probability. So everything works in a probability framework. And then you can say, oh, I have already captured the uncertainty on both the parameter and also on the data. So everything's probabilistic. I have all the uncertainty. But it's only optimal. Sure, it's a probabilistic prediction, but this will only be optimal if your model is correct. And if your prior is correct, which are never correct. How could you have like correctly specify the model? How could you correctly specify the prior? So our models are wrong. And there are evidences why Bayesian modeling or probability cannot save you if you naively just apply Bayesian modeling. For example, we have this recent paper from Google, which says that if you're running a deep neural net, and if you just use Bayesian training to train the this image net level network, it doesn't actually give you any advantage in terms of prediction compared with the map estimate. A more convincing answer to why do we want to use Bayesian modeling is that we want to build a probabilistic model rather than such that it can be generative and it can incorporate regularization and structure the prior. And it also have information pooling such that we can have shared information across different subset of the population in which you might not have enough observations. Often unspoken advantage of Bayesian modeling is that you have simulation of everything. After you have got the inference, you have simulation of the parameter, you have simulation of generated quantity, you have simulation of the predictive quantities. And then with those quantities, you can do everything. For example, in the previous election example, after you got the inference, you can if you fit that using say MCMC algorithm, then you get Monte Carlo draws of all the quantity after inference. And then, for example, on the election day, you see like the election results in some states. How do you get update on the conditional probability? You just do condition. You just look at your simulation draws and conditioning on those draws in which the desired outcome has appear, right? And then you get the conditional update. So for the sake of completeness, I can briefly mention how this election how this election model is constructed, just to showcase how the probability modeling work in practice. So yi is your because the data comes in like different in polling. So for each poll, you have ni, which is the size of samples or the size of population in that poll, and yi would be like, for example, the tendency of the voting tendency for one candidate. Sorry, yi is the number of officials who say that they will vote for one candidate. So theta I represents like the ultimate tendency that you want to capture, that how much proportion of the population would like to vote for one candidate. And we do this logic model for theta I such to transform because theta I is like probability between 0 to 1. And after we do this logic transformation, it becomes an unconstrained parameter. And then we can decompose theta I into different effects. The polling house effect, the polling population effect, you have different modes of polling. It can be internet polling, it can be in person, can be form survey, and you also have non-response biases. And you can, if you are using a probabilistic modeling, you can easily incorporate all these effects into your model and make joint inference on all of them. And we can also use regularization and the structure prior to make your model more robust. So for example, here, when we want to make this parameter inference, they are different in different states. So we, and of course, for some states, you have very few oscillations. And that makes your inference unstable if you just make direct inference. So we can put a prior, a multivariate normal prior that incorporates the state level correlation, such that even if you don't have enough observation in that state, but if you have this correlated prior, you can still make stronger conclusion in that state. Yes.
Can I ask like kind of a basic question about being a Gaussian prior? Like, is it usually done because Gaussians are relatively easy to work with, or is there actually like some kind of methodological reason why it's artificial?
Oh, here, I guess Gaussian is not even really relevant here because here you only want to capture like the correlation. So I guess it's the same to say I just want to incorporate the correlation, and Gaussian just the easiest model in which you can capture both the mean and the correlation. But also here, I mean, I guess it's also because we after this logic transformation, we have already transformed all the parameters into unconstrained space. So apparently, if it's 0, 1, if it's on the probability scale on 0, 1, you shouldn't use Gaussian because Gaussian does not have support on 0, 1. And the second reason why do we want to use Bayesian inference, why we want our Bayesian modeling, is that we often have automated inference or computational tools in Bayesian context, typically some MCMC methods, which I believe we have a class on that in this week. We can also use variational Bayes or mode-based inference, such as Laplace approximation or its variance. And typically, we would be using some probabilistic programming that are such as STAN or PyMC3. which are widely available in different language, including Python and other things. So probabilistic programming just means that you have like this, like for example, the previous probability model, and you don't have to do anything. You just tell the probabilistic programming that you have this model, and then this type of inference engine will help you to make inference, and you don't have to do anything. The last, yes.
So I have like one question.
Yeah.
When we do specify these models, right? Like we then have like specify like prior distribution.
Yeah.
So what is like, some like, I mean, if I had a good prior, then I might have like, solved the problem myself, right? Like this question always comes back to me, like, how do I set good priors? And it seems to like influence.
Oh yeah. So I think some people say, oh, I don't like Bayesian inference because I don't want to set a prior.
Yeah, yeah.
But that does not mean like, but prior is part of a model. And like in the frequency modeling, like in like non-Bayesian modeling, you have to specify your likelihood. The likelihood is just as hard to specify as your prior. Like there's no specific reason why the prior is harder to specify.
But the likelihood is parameterized, right? Like in some sense, those parameters are being learned by the model itself.
Right.
Like in these kind of methods, like I was just wondering, like, is this like, are there like some good solutions here? Or like...
Oh yeah, if you do worry about like oh maybe I want to be safer, then you can run like multi-level prior, such that you have like your prior itself is determined by hyperparameter, right? Then you can make inference on the hyperparameter. So you have hyperprior and prior, and your prior is determined by hyperprior. So in the same way that your prior can be inferred using data. But also, often cases we have like default prior, right? And in the past, I believe people just want to use like a wider prior just to be safe. But I guess now we just more and more realize that we want like the prior to be more informative, just for the purpose of better computation. For example, you can imagine in a neural net context, what if your prior is very wide? On the weight is very wide. Then after the logic if your prior is like normal 0, 10, then the prior predicted distribution on y would be either 0 or 1, right? Because it's logit, inverse logit beta x, and like if beta is very small or very large in absolute scale, then beta x would be very large in absolute scale. And inverse logit of a very large number in absolute scale would be very close to 0 or very close to 1, which is not desired, right? Unless you believe that your predictions are close to 0 or 1. Otherwise, for example, in this context, I don't believe your voting prediction would be very close to 0 or very close to 1. So apparently here, if I use a very wide prior, it's just undesired.
Can you go back to the previous slide? Sorry, the one with the election, like where you have the variables, like the model, the probabilistic model itself. Yeah, so over here, like this is not your prior, right? This is kind of like the.
Yeah, they are like the model, the likelihood.
This is the model. Yeah, but how do we set like priors for like polling house effect and like these seems like kind of complicated. Like how would I don't like have like any intuitive sense like how would I set these like priors on these?
Oh yeah, that in part leads to the main focus of this talk is that often cases there are so much degree of freedom in your modeling, and it's likely that you have different models because you have different priors, you have different prior beliefs, and you either want to select one of them because you don't know which one to choose, or you want to incorporate all of them because sometimes so we want to do model averaging. So that pretty much leads to the third feature of Bayesian modeling is that when we do Bayesian inference, we often have built-in model comparison, selection, and averaging tools. that can help us to do these tasks, often for free.
And also, I think like in the big data limit, it also doesn't really matter what your priors are, right? Like your likelihood term.
Well, if you have fixed configuration space, but often cases if we have big data, we also have big model.
Okay.
So the number of the parameter space is also large, such that you will never reach the asymptotic limit to wash out all your prior effect. So why do we want to do model comparison or model selection or model averaging? Is pretty much because all models are wrong, but some are useful. So we want to select the correct, not the correct model, but the useful model. And later we will see that another interpretation of some models are useful is that indeed some models are somewhat useful. Because in the election forecast example, you can imagine some models are more useful for New York, and some election models might be more useful for Vermont, because they are very different states. How could you have one universal model that is always correct? A model selection just means you want to select one of the models, and you use that as your model. But often that's not enough, because we want to do model averaging, we want to do ensemble, we want to do meta learning. The idea is that if you have already designed lots of models, you want to incorporate all of them. And also, we have this garbage in, garbage out cliche such that if you have a bunch of horrible models, that even if you average over them, it's still horrible. Is that really the case? Actually, that's not really the case, right? Because, for example, in boosting, you can have like many like horrible models, but after you sort of average or like mix over them, you have a much better result. So if you have garbage in, you have garbage out. But if you have not many garbage in, maybe you have something better out. So the workflow of a typical Bayesian modeling would be that you gather your data and you have like you fit some models and you get the inference and you make a model assessment on some desired quantity, and then you look at your model and you or other alternative models, and you choose what to and you run this model comparison or model selection scheme, or you can run model averaging and you generate some better models, and then you look at the model again to decide if the model is good enough, and if it's not good enough, you can decide whether you want to improve the model or you can collect more data. So now I can talk about the technical detail of how to do model selection and model assessment. But before that, it's important to distinguish a few conceptual difference in Bayesian modeling, and it's typically called M views, and we typically have 3 M views called M closed, M complete, and M open. So M closed means that you believe one of the model in your model list is correct, but you don't know what it is. But you just know one of the model is correct. And M open means that you just don't trust your model because the true data generating process is just too complicated, and you don't believe you can specify that, or you don't want to because it's too complicated. For better communication, you don't want to specify a too complicated model. And M complete means that you believe that the model in your model list is all the models in your model lists are wrong, But still, you want to use some of the model as a proxy of the truth and project your belief of the underlying truth onto that belief model that is in the model list.
I can get the difference between M complete and M open.
So M open just means you just don't believe any of the model in the model list. And of course, you still have to use those models, like that's all you have. But in the end, for example, when you do model selection, you don't believe any of the model is a true model. You just acknowledge that some of them are useful. And when you have M complete, even though you don't believe them, even though you don't acknowledge that one of the model in the model list is correct, you select one of the model as the proxy of the truth. And when you do model averaging, you can use that that the best model, like as if it's a correct model, and you can do projection inference. It's more subtle difference on the specific technique that we would be using in terms of model comparison. So in the M closed view, it has been familiar that we can often use marginal likelihood or Bayes factor or Bayesian evidence as a way to choose a model or to do model averaging. The idea is that the posterior inference is the likelihood times prior divided by the evidence, and evidence just Py, right? It's marginal likelihood. The marginal likelihood of a model is just the prior of the model times the marginal likelihood. And if you have many models, then the posterior inference, the posterior probability of the model is the marginal likelihood times the prior normalized over all models. And this Py given M is of course just it's just here, right? You have the it's just the likelihood and the prior, and you integrate out over the parameter, which is why I named marginal likelihood, because it's a likelihood evaluated under the prior. The advantage of the marginal likelihood is that if we are doing model selection based on marginal likelihood, then it's always consistent, even with nested models, which means you have like a sequence of models and they are nested, which means the previous model is a special case of the next model in a sequence. And it's always consistent, which means you can always select the correct model. Yes.
One question about the notation, like what is the Y with the builder on top?
This one? Oh, so I here just mean like the next data or like future data, future unobserved data.
Okay.
The data in which you want to make prediction.
And Y is what we already see. Like,
Yeah, Y is like observed data.
okay, so this could include like the features as well.
Yeah, like X.
This is everything.
Like well, yes, like X is I just omit X. Like X your feature. Yes, it's always given. Like all the likelihood is conditioning on X. The nice thing of the Bayes Bayes factor or model selection is that it's consistent and it automatically prefers simple model. Because when we look at the evidence, the P given the model or hypothesis I, it's likelihood integrated out over the prior, and you can do a local Laplace approximation if you want. It's the likelihood valued MLE times the doing Laplace approximation. It's the probability of the prior probability of that MLE times the, because you can imagine so Laplace approximation then involves then what's this it's the height and the volume of that Laplace approximation, right? And the height is just the prior probability of that MLE, and the volume is you can approximate the volume by the variance, the standard deviation of the MLE in the prior distribution. So if you have a simple model, then this quantity would be large, right? Because this quantity would decay if your dimension if the dimension of the prior distribution is very large. Yes.
Just to clarify, so this is like a sequential process that you get your posterior or are these examples?
Yeah. So I haven't talked about Bayesian model averaging. So here I'm just saying how to do marginal likelihood, and I'm saying it prefers simple models. And then then the classic meaning of Bayesian model averaging is that we weight each model according to their marginal likelihood, because that's how we compute the posterior probability of each model. So yes, it's the inference of the model and the inference of the model weight are separate. You compute the inference and then you compute the weight. Like these two steps are independent. So that's Bayesian model averaging. It's like any quantity you want to compute, you compute the conditional the quantity inside each model, and you also compute the weight of that model, and then you average over this thing. And the weight is a deterministic procedure that's computed using marginal likelihood.
Just to compare with like ensembling, right? Like the frequentist kind of approach. Over there, you would also have like these predictions, like the posterior predictions. But in some sense, our weights are not like, our weights are like some heuristic instead of having like margin like.
Right.
Is that the right way of thinking about it?
Right. Right. Yeah, I don't think I don't think there's a strict counterpart of what Bayesian model averaging would mean in a frequentist context. Because if your prior is, because you can imagine the frequentist inference is just Bayesian inference with a fat prior. But if you have a fat prior, you can't really compute this quantity, right? So the term would become 0, right? But if all the previous slide is talking about the M closed view that you believe one of the model is correct. Otherwise, it just makes no sense to talk about the posterior probability of a model, because you just don't believe, because the posterior probability of the model means the probability of that model is correct. But in an M open view, you don't believe any model is correct in the first place. It just makes no sense to compute the probability of the model being correct. And there are some reasons why the Bayes factor or the marginal likelihood can be misleading or even useless in the an open context. One is that it's quite sensitive on the prior. It's just pointed out that if you have a very wide prior, then it basically becomes 0. And to see that, you can just use this simple example that if you have a logistic regression, if the likelihood is just like inverse logit a plus bx, and now you have 2 prior. One is like beta is normal 0, 10, which is a wide prior, right? And another prior is like this beta in the model is normal 0, 1000. This is the standard deviation of the prior. So these 2 prior are basically flat. Like they have no influence, they have no difference in your parameter inference, because they're both flat, right? Like if x is already standardized if x has already been standardized to have standard deviation 1, then they can't have any effect on your inference. But if you compute marginal likelihood, it will change the Bayes factor by a factor 100. Because when you compute the marginal likelihood, you have the prior probability, you have the prior term, And the prior term of this thing is 100 times smaller than this term. So automatically you would prefer this model 100 times better than this model, even though they have no influence on your parameter inference or on your prediction. So that's how can that be? Like you have two models and they are essentially the same, but you prefer one model 100 times bigger than the other model. That's just not desired. And slightly related to this problem, we have this. We can also present the similar problem in a quantum physics context. Suppose you have this double-slit experiment, which must have been familiar. So if you have two slits, slit 1 and slit 2, and let me just call the image on the screen as like Y, right? Like so Y is just the pixels on your screen, and Py is the distribution of the image on the screen, like after the two slits, because it's a distribution, right? Like on the screen, you have image, which is distribution. You call it P1. And now if slit 1 is open and slit 2 is closed, you have one image. Then just call it P1, 1. And now slit 1 is closed and slit 2 is open. You do the experiment again, you get another image. That's P2, 1. And now both slits are open. We have a third image, which I call it P3Y. That's an image. Now, if we do the marginal conditional decomposition, as we have done in the previous slides, we would have P3Y equals Px equals 1, the probability of slit 1 times the conditional probability, Y given x equals 1, plus probability of x, the slit 2, times the conditional probability, Py equals x equals 2. That's P2, 1. But it's obviously wrong, right?
But this violates the independence.
What's independence?
This is kind of assuming that, I mean, there's no independence between the slits, right? That's important.
No, but when you run this Bayes formula, there's no requirement on independence. What do you mean? What do I even mean by independence? What's Px equal? What do I mean by independence between Px equals 1 and Px equals 2? Like there's no independence. There are two numbers. There's no independence between two numbers. The independence is between two random variables. But here x equals 1 and x equals 2. They're just two numbers.
I meant like the two factors, like slit 1 and slit 2, the probability of Y conditional on those are not independent of, you can't decompose those into two. Okay, so we have like two states, right? Like slit 1 open, slit 2 open.
Yeah.
I'm saying probability of Y conditional on slit 1 comma slit 2 is not like, you can't factorize those into probability of Y conditional slit 1 times probability of Y conditional slit 2.
Oh yeah, of course. That's what I'm saying. Like it's wrong. Like
Yeah.
in this context, we just can't apply Bayes rule. Like it's just wrong. Yes, we know it's wrong.
Yeah.
But it's as wrong as the previous slide that in this open context, naively applying Bayes rule doesn't actually help you. It actually makes things worse, right? Because you get the wrong inference. And if we are using Bayes factor in model averaging context, in this model averaging, in Bayesian model averaging, then model averaging essentially becomes model selection, because the marginal likelihood, because the probability of if the models are separable such that they don't overlap, then one of the model would essentially have weight 1, and all the other models would have weight 0. And here asymptotically means n goes to the number of examples n goes to infinity, then Bayesian model averaging becomes model selection because you just pick one model. And that model can be quantified by the model that has smallest KL divergence to the tributary process. But that's not really good, right? Because my goal is to do model averaging, but in the end, all I get is just model selection, which is bad.
But I thought, I mean, the reason we want model averaging is because we are in the low data limit, right? So in the high data limit, like it doesn't really matter what happens. I thought like
Oh, if I have a lot of data, I also have many models. Like I still want to do ensemble. I still want to do meta learning because that helps the expressiveness of the modeling. But anyway, it's just wrong because like, why do I want to select one model? My goal is to do model averaging. Why do I just pick one model? Like if my goal is just to pick one model, why can't I just run model selection in the first place? And in the more realistic context, we have this recent PNAS paper that's saying in biology, if we are using Bayesian model averaging to average over phylogenetic trees, it often cases just pick one tree, which is arguably wrong because that's based on the incorrect usage of marginal likelihood, because none of the tree should be believed as a correct nature.
so the difference, I think I understand, like over here, like even in the infinite point limit, your models are always misspecified.
Right.
Right.
Yeah, I mean, I just can't believe why, like with more data, there's actually it's even harder to specify the model because you have more data, you have more pieces of information, it's harder to specify. So in the M-open view, we just abandon this Bayes factor. Like the Bayes factor is not relevant in the M-open. And instead, we want to use Bayesian decision theory. And to use Bayesian decision theory, we have to introduce the what metric we would be using when we evaluate the prediction. So typically, we will be using some scoring rule. So the posterior predicted density is the feature data given the training data. And that's the likelihood given the parameter and integrated over your posterior inference given training data. So that's your posterior inference of the future data. And a scoring rule is a way to evaluate how good this prediction is. This is a probability. How good this probabilistic prediction is on the future observed data. So the scoring rule is a bivariate function that takes the input of a probability and the observed data to a number. And a scoring rule is associated with a divergence, which is divergence is also a bivariate function that takes a product of two probabilities into a positive number, because we can always define a divergence as scoring rule minus, the scoring rule of itself minus the scoring of your prediction and your true process. Yes.
I didn't completely get like second argument of S is not a contribution.
Oh, here I'm just using this convention that because here it's like it's Y, right? Like, but so because your prediction is a probability, but your observed data is a number. Then how do you evaluate this on the true process? You just integrate out this thing. So it should be an integral. So the scoring rule is just of this is a true process. This is my prediction, and my utility function is just the scoring rule. The average of the scoring when averaging over the true process. And the scoring rule is called proper if SQQ is larger than SPQ. That's understandable because if your prediction is attributed during the process, it should always have the largest scoring rule compared with any other predictions. And the only strictly proper local scoring rule for continuous outcome is a logarithm score. That's why it is widely used in almost all inferences. So that is, if you have a prediction and you have an outcome, then you evaluate how good your prediction is through log py is a prediction, y is the outcome. And associated divergence with a log score is a KL divergence, which also justifies why KL divergence itself is widely used in machine learning or in Bayesian statistics.
Can you give some intuition why? Like it seems like why does that be logarithm? Like, it could be so many other things, which are also smooth and also satisfying.
Yeah, but it turns out you can prove that the logarithm score is the only proper scoring rule that is local.
What does local mean?
So local means that local means SPY only depends on PY. And the evaluation of the prediction only depends on the evaluation of the prediction evaluated at the observed data, not at other data. So in a later discussion, I would be focused on logarithm score because it is the only proper scoring rule.
Kind of related is in this family of F divergences, right? Like when we have instead of log, we have like F, so we get like total variation, we get like F family. So is there like, I mean, intuitively, I can't figure out like why those are like worse than. Yeah. Okay, maybe we can like I can ask you later.
Right. Okay. So we can talk about the expected utility of a prediction. That is expected log predicted density. Because so again in the PT y delta kilo y is the true-to-the process of the future data given the observed data. It comes from nature, like we don't know, but we know this. That the data itself is a probability, right? So that's the truth, the PT, the T denotes the truth. Y delta given y, and you evaluate this your prediction, log py delta given y, given your model, and you integrate out over y delta. So that's the expected log predicted density, ELPD. We don't know how to compute this quantity, right? It's like it involves PT, which we don't know. If we know PT like delta given y, then I don't have to run my model. I just use that as my prediction. But luckily, we can still compute this thing using observed data, and typically we would be using, for example, cross validation. Because even though I don't know PTY delta given y, but I have like in my observed data, yi given y minus I is a proxy for this quantity, right? So what I can do is I can compute the observed predicted density of yi given y minus I, which means when I do the inference for each yi, I compute this quantity, that is yi given theta m is model, and theta is a parameter, and instead of training theta using other data, I train theta using the cross-eye data, the leaf eye out training data. Then I integrate out over. I get this leaf eye out predicted density on the eyes observed data, and I do this n different times on all the observed data points. And then I can compute the ELPD loop, which itself is an asymptotically unbiased and consistent estimate of ELPD, assuming the data is conditionally IID or exchangeable. So here is an illustration example. If we have this linear regression, y and x, and what we would do is, well, if you just run the Bayesian inference, you first have this the posterior mean, right? This like the posterior mean of your prediction, the red line, and you also have posterior jaws, but you can't use this posterior jaws to evaluate the observed data because that's overfitting, right? When you use this to evaluate how good the prediction is, you already see this, you have already seen this data. Can't use those things to evaluate how good your prediction is. That's overfitting. So what we can do is we retrain the model. For example, if I want to evaluate how good my prediction is for this particular data point, I would retrain my model using all the data except this data. I train my model again, I get a different curve, which is a green line, and then I get a predicted distribution, the Levi-Nut predicted distribution, which because everything is probabilistic. So you have a Levi-Nut probability distribution, which is a green curve, and you evaluate how good the prediction is. That's the log predicted density of this data point. The nice thing here is that the ELPD is a summation over n different terms, right? It's like for each data point, you can compute this ELPD loop quantity. So you can get the standard deviation of your of the ELPD loop quantity because it's summation over n terms. Then you just compute the standard deviation, and then you can use this standard deviation in your model comparison. Another related quantity is you can compute both the ELPD, Levi-Nut ELPD, sort of the expected testing error, testing utility, and the observed LPD, that is just you don't have this Levi-Nut procedure. You just run a model and you evaluate how good the model is. And the difference between them would be the effective number of parameters. And you can actually prove that in expectation, LPD is always larger than ELPD. So you always have a positive number, but the difference is always a positive number.
I didn't get the, like, what is the subtraction given? You said you subtract the LPD.
Yeah, LPD minus ELPD2, which is this line. So you have like this. So you compute. So ELPD is just like you use Levi-Nut training to train the model n times, and you evaluate each data point using the Levi-Nut predicted density. You get one number. LPD is you don't have this Levi-Nut training. You just train the model once, and you evaluate how good each data point is, and you sum over them. You get another number, and you can prove that mathematically this number is always larger than this number. And the difference between them is just the effective number of parameters of the model. So this is a useful way to quantify the complexity of the model.
I thought, I mean, in some sense, it's capturing the robustness of the model, right? Like if I don't observe this data, if I don't observe this one training point, like how much error is there at the training point in my predictions? Is that a good way of thinking?
Yeah, I guess point-wise, it's a way to evaluate how influential that particular data point is. But if you summarize over all the data points, then it becomes a metric of the model complexity.
Okay.
So which now, of course, this effective number of parameters is not necessarily the same as you just count the number of parameters in the model, because maybe you have very large neural net model. You have thousands or tens of thousands of weights but the effective number of parameters is not that large. The practical difficulty of this procedure is that cross-validation is too slow. We can't just rerun a model n different times. That's just like, we just can't do that because it's sometimes even too slow to just run the model once. So we want some fast approximation of cross-validation such that we only fit the model once. And the blessing of Bayesian modeling is that often cases, the leave-one-out cross-validation is cheap or almost free compared with training cost. The idea is that we can use importance sampling because in the only difference between the leave-one-out, the difference between leave-one-out predict the difference between the parameter inference of the leave-one-out distribution and the full data inference of the parameter inference is very small, right? And we know exactly what the difference is. The leave-one-out, this is the full data inference, theta given 1. And this is the leave-one-out parameter inference, theta given 1 minus 1. And what's the ratio between these two? It's just the likelihood of the ith term, right? So we know exactly what the difference is. It's just the inverse likelihood. So in probability, if we have access to one distribution and we want to compute the expectation of a slightly different distribution, what we can do, we can just run importance sampling, and the importance ratio is exactly inverse likelihood.
Here, the importance density is the same, has the same expression as the likelihood.
The inverse likelihood, yes. So that becomes the importance ratio.
So the importance density from what you're sampling, like I mean, you need to find out importance density.
Oh, we just train the model once. So for you train the model once. So here theta ks, like because you have k models. So for each model you have like s jaws, like one to like because you are running MCMC algorithm or some variational base. So you have like say like 3,000 jaws. So s equals 1 to 3,000. And for each of theta s, you can evaluate this likelihood, inverse likelihood, and that's the importance ratio of that theta s. So theta goes 1 to 3,000, and for each theta you compute this importance ratio. That's RIS. Now it depends on I, right? Because like when you compute different data point, you have different importance ratio. You have to compute this importance sampling procedure for each data point. But it's relatively cheap because the cost here compared with MCMC sampling is negligible. But the problem is that it's not stable so to show why it's unstable, we can look at the general theory of importance sampling. In importance sampling, the goal is to compute expectation of some quantity under a distribution P. But instead of sampling from P, we can only sample from a proposed distribution Q. Now, so what we can do is we compute the importance ratio R equals the target distribution divided by the proposed distribution P over Q, and that becomes your importance ratio. And then you weigh the H theta, the function, by this importance ratio, and you do self-normalization when you draw theta from Q, the proposal. Now, this importance sampling estimate is always consistent and asymptotically unbiased as long as P and Q have the same support. But the importance sampling can't have large or infinite variance if P and Q differ too much. And we can actually quantify the difference. We can actually quantify the difference using the KL divergence between the proposal and the target distribution, and you can prove that the effective the necessary and sufficient sample size to ensure your important sampling to have good large deviation probability would be the EXP of that KL divergence. And you can imagine if they differ too much, then the EXP of this, because it grows exponentially. So as long as they differ a little bit, then the effective sample size, the required effective sample size becomes too large to be achieved in practice.
But the previous case, the P and Q aren't expected to differ that much, right? Because it's just the one out that you miss.
Oh yeah, so the difference,
So,
the difference is this term, but we don't know how long. But this term can still be very like. There's no guarantee that this term is give you good stable distribution. Like it can even have infinite variance. Why this term has to have finite variance? So in a recent paper, we addressed this problem by stabilize the importance ratio. For example, you can fit a parametric family to the ratio. For example, a generalized Pareto distribution, and replace the ratio by the expected ratio. Then becomes a practical pipeline for Levi-Nod cross-validation. Because all you do is to fit the model once, and you collect those theta jaws. And for each theta and each data yi, you compute the importance ratio, which is the inverse of the likelihood, and then you run this Pareto smoothing to stabilize the ratio, to make it always have finite variance, because you replace the ratio by the expectation in a model, in a generalized Pareto modeling. In a way, you truncate to the extreme large numbers. And then you only need to fit the model once. It also gives you good diagnostics, because we can quantify how good, how reliable your importance sampling is by the shape of this generalized Pareto distribution when you fit the, because you fit the, you model the importance ratio by a generalized Pareto distribution, and the shape parameter of that generalized Pareto distribution gives you good diagnostics. Because the shape parameter in the Pareto distribution tells how much variation you have in the tail. And this, of course, has software implementation in both R and Python, and it gives you automatic Levi-Nod cross-validation approximation that only requires you to fit the model once. So this is, but the previous slides are only about IID data, because we do this exchangeable n terms, and we sum over these n terms. Of course, data is not really IID in practice. We have time series data, we have hierarchical data, we have spatial data, we have panel data. So CV itself can be quite complicated in these cases, and you often have to treat this different scenario on a case-by-case basis. For example, here the simple example that we have, we want to predict, this is actually the data from the weight of rats on different age, and so each line is one rat, and you measure the weight of that rat at different age, which live 3 days. So you have this is the data, it's panel data, right? You have different subject, and each subject is measured over time. How can I do that cross-validation here? Can I just leave one data point out? Yes, you can, if you believe the data is actually exchangeable. And you can also do one step ahead prediction, that is, each time you move one data out, and you move the last data out, and you use all the previous data as training data to see how good your prediction is, and you repeat this on all the previous days. So this would be useful if your final prediction task is to predict how good the weights of these rats are in the next day, right? Now, can I leave one data point out? You can still, yes, you can still do that, but then you just like do the similar things, but each time instead of doing leave the last day out and make one day ahead prediction, this time just like randomly drop one day and run cross-validation on that day. And this is also a useful metric. If your goal is to make prediction on an intermediate day that comes out in a future experiment, you can also leave one rat out if your goal is to make prediction or inference on a new rat. Even in this toy example, you can have different randomizations, and the different cross-validation scheme amounts to different prediction tasks, which typically is specified by the user. So there's no universal way to do cross-validation. Depends on your prediction task. And this leave-one-out cross-validation is often related to the information criterion, different IC like AIC, BIC, or WAIC, the widely applicable information criteria. So AIC is a frequentist way to measure the model performance, and BIC is a way to approximate the Bayes factor, the Bayes marginal likelihood. WAIC had the same assumption as leave-one-out cross-validation, but in a way that if we are running this Pareto smoothing point sampling, it's more reliable than those information criterion-based metric, because they often make some normal assumptions. And this, when you are running this leave-one-out cross-validation, you don't have any normal assumption, and also more accurate. We can also draw the connection between cross-validation and marginal likelihood. So it turns out the marginal likelihood itself can be viewed as an average of leave P out cross-validation when P is summing over 1 to n. So if P is 1, it's just leave one out cross-validation, right? So that gives you one metric. And you can also say, oh, what if I leave 2 data point out? That's leave 2 out prediction. You can also leave n out prediction. Well, now what's leave n out prediction? That's just prior prediction, right? You don't have any training data. You only use your prior to run a prediction, but that's still a prediction. So you can do leave n out prediction. And when you sum over 1 to p equals 1 to n, it turns out this quantity is the same as the marginal likelihood. So in a way, it's that shows why the marginal likelihood is not necessarily the most relevant quantity for prediction. Because why should I care about leave n out prediction? That's just very irrelevant. So the last piece I want to mention is stacking, or in the universe of this model selection and model averaging scheme, there's a last piece that how do we do model averaging in the M-open scenario, that if I don't believe any model is a correct model, what I should do to do model averaging. I can't use Bayesian model averaging because that's M-closed. The idea of stacking, of course, traces back to David Warpit and Leo Bremen in the 90s. Even though it's an old idea, but it's still often the winner of recent competitions, for example, the Netflix competition, and also the recent causal inference competition. So it's still a relevant idea, even in modern days. The idea is simple. We want to optimize the model performance. We want to optimize the model weights to minimize the cross-validation error. Because and then you have different training algorithms. They can be decision trees, like whatever training algorithm you want to use. You have a second layer model. This layer model is determined by the stacking, which is to linearly average over the prediction, and then you choose a weight to minimize the cross-validation error. We can certainly apply this idea to Bayesian modeling. In Bayesian modeling, there's no, you only need to a little bit modification. So for each model, you have the prediction on the I theta point to compute the Levi out log predicted density. And then if you have k different models, you want to optimize over the weight such that the combined predicted distribution, which is summation over wk times p yi given y minus I, has the largest log predicted cross-validation log predicted density, subject to the constraint that the wk has to be simplex. The wk has to be simplex such that your predicted distribution is a probability. And asymptotically, you can show that this procedure is give you consistent estimate. So this idea is not only useful to combine different models, it can also be used to combine different modes or different rounds of computation. This is relevant because many learning algorithms in modern statistics, yes.
How is this like different from ensembles? Like the weights are just shared, right? If you go back to like previous slide. So there are k models and there's k weights, right? So this is like very similar to ensembling in like the standard.
Oh yeah.
Yeah, this is.
Yeah. Sure, it's one ensemble too. It's literally one of the ensemble algorithm. We can also use this idea to combine different modes in Bayesian computation, because many learning scheme in modern statistics involves multimodal landscape. For example, a deep neural net, it often contains many modes. And if you really want to sample from the exact posterior distribution that contains all the modes, it's very hard because the MCMC algorithm often have difficulty jumping between one mode to the other mode. You can have some customized sampler, but that often takes infinite time to mix, to jump across all the modes. So one practical solution to solve this multimodal sampling challenge is that instead of jumping between the modes, we just run parallel inference and sample all the modes, not necessarily all the modes, but like as many modes as possible. And then you run fast Levi-out cross-validation on each mode to evaluate how good each mode is in terms of predictive metric. And then you run stacking to compute the optimal weight of the modes. It's not the weight of the model, it's the modes of the modes. And then you combine these modes. So that becomes a practical solution to multimodal sampling. It just don't need to do anything else, just run ensemble of the modes. So we did some experiment on how to use stacking in multimodal sampling. So this is an LDA, the latent Dirichlet allocation example. It's often multimodal, and if you're running deep sampling, you don't even know how many modes you have already sampled from. Because when you run deep sampling, you often just run one chain. You only have one run. You don't have parallel evaluation. So but we can do many times. We can run many times, and indeed, each time you get a slightly different. So each green dot is a different chain. Markov chain. When you run different chains, you typically have different results, but that's okay. We just run stacking and we combine them, and that often gives you a much better result than any individual chains. So you just have better fit of the data. So this is a Gaussian process example. Gaussian process can also be multimodal. For example, here, if we look at the margin distribution of the rho is the length scale, and alpha is the scale of in a GP, and using exponential squared kernel. It actually has two modes, right? So what I can do, I can run stacking to combine these two modes, and actually gives you better result than just naively using the exact. It turns out to be better than running Bayesian model averaging of these two modes. Another often multimodal landscape comes out in sparsity regression, for example, the host regression, a useful model for enforced sparsity in regression. It has two modes, and it has two modes for each parameter. So if you have a genome example, you have thousands or even millions of genes, and you would have 2 to the power d modes in theory. So it's very challenging for MCMC or VB to jump over that 2 to the power million of modes, but you can still run stacking. And we did that on some toy examples, and you can see how it turns out you not only get good prediction, but also it also helps you to make parameter inference that can approximate the bimodal distribution, even using very simple mean field Gaussian approximation in variational Bayes. The last piece here is hierarchical stacking. The idea is that when we run model evaluation, we average the predictive ability over all the X. But that's a little bit naive, because we know the model must have different predictive ability for different X. If I have an election model, how can a model be the same predictive in New York and in Vermont? No, it's just the model must be different in different configuration space that is determined by X, right? So a natural idea is that if some quantity should vary in the population, then it should vary. And here, all models are wrong, but some models are useful in some places. So we want to design a model averaging tool such that the model weights itself should vary in the population. And we can turn this problem into a Bayesian estimation problem, because now the goal is to make an inference on a weight function. So the goal is to make an inference on a function, right? And the function takes space of X into a simplex. It generally have infinite dimension object because it's a function. Function is infinite dimensional object. But that's okay. We just run Bayesian inference, and you can incorporate any familiar Bayesian prior on the weight on this infinite dimensional function, such as Gaussian process on Wx. So this is like how we run this inference. We compute the posterior we view this W because you want to make inference on a function. But in Bayesian nonparametric, it's easy to make inference on a function. You just equip this W with some prior, for example, a Gaussian process prior, and this is a likelihood which is constructed using the VI out predictive density, and you combine them using this weight, which is a function of X. And this hierarchical stacking itself is also a showcase of why a Bayesian inference can often make prediction or otherwise black box machine learning algorithm more robust. Because here the goal is to make inference on a function, and if I don't have Bayesian inference, it's often a very noisy estimation. But now if I equip a better prior, such as Gaussian process prior, then the estimation is more stable. So this is the same example as before, that Gaussian process regression, that I find two modes, mode 1 and mode 2, in this length scale, and this is length scale. Now this is landscape, and length scale of the Gaussian process kernel, and this is the scale of the kernel. I have two predictions. I want to, which is generated using mode 1 and mode 2. This given these two hyperparameters, the mode of the hyperparameter of two modes. I want to average over them. But instead of having a universal weight for one model, now I want the weight itself to be a function of x. So I can model this weight by a Gaussian process prior. So this is the inference result you get when you this is the weight. The weight itself is determined by another Gaussian process prior. And it turns out if you run this Gaussian process prior combined distribution, it gives you even better results than just running stacking.
Sorry, why is that here you want the weights we variable in X too?
Oh, because you have two models and you have two predictions, right? But then they must have different prediction in different areas. So you think, so for example, here it turns out like for example for this particular data point, for this region,
It's just
model
like
one is
small decision, basically.
sorry?
It's just a decision. It's just a decision.
Yeah, but like, so like, for example, here, like one model is better than the other model. And here, the other model is better than the other model. Like, yes, a little bit here, yes, because these two models are essentially very close. But in some other, in other contexts, like you might have different models. They have different performance in different regions. So, for example, in an election forecast, we have a bunch of models. Some of models are fundamental model, and some of the model are the previous probabilistic model that can have different prior structure or different time series structure, and have some of them might incorporate other informations too. And then we run hierarchical stacking to learn a state-specific weight. And we also incorporate the prior such that the similar states or neighboring states should have similar model weights, which itself can be incorporated using a multivariate normal prior after the Lodge transformation. Then it turns out this hierarchical stacking is better than stacking, and stacking itself is better than model selection. We can also look at the performance in different states. If you have very few poles, like then hierarchical stacking is as good as stacking because you have very small amount of data. So have a more expressive model averaging doesn't really help you. But if you have many observations, then having hierarchical stacking would be better than stacking because you want the model weight to vary in the population. And I don't have time, but I can briefly mention that the stacking is certainly related to the idea of mixture of expert, which is another old idea. But the difference between stacking and mixture of expert is that mixture of expert, you train the model weight and the model at the same time, whereas in stacking, you train the model first and you run the model, you run the stacking afterwards. So in a way, it's computationally cheaper. And also you can't really use mixture of expert to combine different modes. Like what do I mean by I have an expert and in each expert is a mode? You don't know those modes when you train the model, before you train the model. And another idea is like when either in mixture of expert or in stacking, we always use a mixture to combine probabilistic predictions. And that's another degree of freedom that you can change, because mixture is just one special case to combine models. You can use other operators to combine probability, such as geometric bridge or even quantum superposition to combine two distribution. And those operators are nonlinear, which has the advantage that you can go deeper, right? Because if you have a mixture of expert or stacking, which use a mixture, then no matter how many layers you go, it's always a mixture. You don't have too many gains from that. So this is an example in which we use quantum superposition instead of mixture to combine predictions. And it has an extra advantage that your final prediction can often cases be unimodal, whereas in mixture, it can often cases be two bimodal prediction, which is undesired. And the final open question is that when we are running this model averaging or ensemble methods, it's not really for the purpose of interpretation, right? So, and then in the end, we only learn the model weight, not really learn how to interpret the model. So that's still lame. It's like the current, what an AI can do when the AI do these statistics is just to learn the parameter, not really to learn the model. So, so for example, in time series, we have AR model, the autoregression model, and the MA model, the moving average model. But we also have AR-MA model, the sort of the model expansion of AR and MA. But now, if I just run stacking on like AR model and MA model, or if I just run like mixture of expert or like boosting or whatever, you can't really learn the AR-MA from these two models, like AR and MA, right? So it's still an open question of how do we want, how like a real AI should do that, right? Not just to learn the parameter or learn the model weight. It should actually learn a new model for you. But it's still for future research directions. So here's a few take-home message. One is that cross-validation is good. If you don't trust your model, you should always use cross-validation-based metric rather than the Bayes factor or marginal likelihood, which is often too sensitive. And in Bayesian inference, the leave and out cross-validation is free or fast if you use good approximation. And different CV amount to different prediction tasks. Model averaging is often better than model selection, and local model averaging is even better than universal model averaging that has the same weight in a population. And model averaging itself can solve by Bayesian inference and incorporate Bayesian structure priors. So that's it, and this is the list of readings that you can read from, and my office is on the 3rd floor of 162 in CCM. So if you have questions, you can ask me here, or you can ask me in person in my office.